Today we have Mauro Sozio from Telecom Paris Tech, and he's going to give a talk about fully dynamic K-center clustering, which is an interesting version of. It's a well-studied clustering problem, but he addressed the more less studied fully dynamic version. So previous results were mostly about insertion only or other variants, and this is about the most general streaming setting.
All right, thanks. Thanks, Alessandro, for the introduction and for giving me the opportunity to present this talk at Google. Thanks, everybody, for coming. All right, so I guess I don't have to convince you here at Google that we have a lot of large scale data sets. So, for example, here we have the YouTube, right? Twitter, internet, the human brain, right? And data sets also evolve over time. The large scale aspect and the dynamic data are one of the main things I'm interested to deal with on these days in my research activity. Yeah, right, so some figures, I guess here at Google you might have more up-to-date figures, right? Google processes over 40,000 queries every second, while more than 400 hours worth of YouTube videos are uploaded every minute. So feel free to correct me in case these figures are not accurate, right?
I don't know. Right. Do you know? I actually don't know.
Not at liberty to say.
I was going to say, if we did that, I'm not sure that we're allowed to comment anyway. So. If we did know, we might not be able to tell you.
Anyway, all right, so I guess 2 billion Facebook users and more than 6,000 tweets per second are posted on Twitter, right? Yeah, so we're really dealing with large scale and dynamic data, and we would like to develop algorithms that allow us to make sense of this tremendous amount of information evolving over time. All right, so what I'm going to talk about today is about fully dynamic K-center clustering. This was presented at WWW this year and also was nominated for the Best Paper Award. In the end, we didn't make it, so it's nice to be nominated at least, right? All right, so there are other works that we did right in this direction, and some of them have been partially funded by a Google Faculty Award, and some of these is also in collaboration with Alessandro. And today I'm going to talk about the second one, right? So fully dynamic K-center clustering. All right, so what is this problem about? I guess some of you already work on this problem, right? So maybe doesn't need too much of introduction. Well, clustering is widely used technique, right, for exploratory data analysis. In this talk, right, we are concerned about maintaining a good clustering of highly dynamic data, for example, data from social networks, biological networks, or also transportation networks. So, for example, here, again, YouTube, geotagged tweets, car trajectories in Milan. These are all highly dynamic data sets, and we would like to maintain a good clustering of these data sets as they evolve over time. All right, so definition for K-center clustering. Some of you already are familiar with the problem, right? So what is our task, right? So we are given a set of points and an integer k, and we would like to find the partition of these points into k clusters, and we would like to find also k points called centers, so as to minimize the maximum cluster radius, right? So the maximum cluster radius is defined as the maximum distance between points and their centers. Okay. All right. So distance function can be Euclidean distance or any other distance function. All right, so let me start right with a simple greedy algorithm for this problem. It's very simple, so I thought I would maybe discuss about it, and also nice as a warm-up. All right. So the problem is NP-hard, and it's actually NP-hard to have an approximation better than 2. So right, this greedy is actually very simple and is the best we can do unless P equal NP. which is pretty nice, I think. Okay, so let's see how the algorithm works. So we pick one point. So X is our set of input points. So we pick one point arbitrarily, and this becomes the first center. Okay. Now, at each step, we pick the point that is further away from the points that have been selected so far. And the distance between a point and a set of centers is equal to the minimum distance among the centers. Okay? So at each step, we pick the point that is furthest away, and the algorithm terminates as soon as we have k clusters, k centers, or we have selected all the points, right? Which is maybe the trivial case when we have only k points in input. This can happen, right? Okay, so once we have the k centers, we can easily create the cluster by assigning each point to the closest center, and then we end up with the k clusters. So very simple, and this gives us a two approximation guarantee. Right, very quick proof, right? In order to see this, right? Let's consider the k centers that have been selected, and let's consider a k plus one center that is at maximum. Sorry, k plus one point that is at maximum distance from the k centers. Okay, so let the mean be the minimum pairwise distance among all the k plus one points. So there is no clustering with maximum radius at most d mean divided by 2, right? We have k plus 1 points that are a minimum pairwise distance d mean. So if you want to have a cluster with k centers, cluster with k clusters, then at least 2 points should end up in the same cluster, right? And then this cluster cannot have a radius smaller than d mean divided by 2, right? So this basically gives us a lower bound on the optimal solution. Moreover, every point is a distance at most d mean from the closest center, okay? And this follows from the fact that this quantity, max dxc, is non-increasing throughout the execution of the algorithm, right? So all points that are not clustered will be at a distance at most d mean from the closest centers, right? And then we can show, right, that our clustering has maximum radius d mean, and we show that better than d mean divided by 2 is not possible, and this gives us a two approximation. Okay? So very simple algorithm, very simple proof, and this is the best we can do on LSP equivalent. That's interesting, nice. Okay, so now maybe I open a short parenthesis. I would like to argue that this problem is also very useful in practice, and it enjoys a nice property, in my opinion. So you can find so-called well-separated clusters, okay? Which is nice. So what is how do we define well-separated clusters? So we say that C1, Ck are well-separated if I take 2 points in the same cluster, then their distance is smaller than any other 2 points into different clusters. Okay? Okay? So if this is true, if this holds, then the clusters are well separated. Okay? So another way to see this, right? This is equivalent to say that 2 points are in the same cluster if and only if their distance is smaller than the maximum diameter of the clusters. Okay, so I think it's a nice property. I think it's a very simple case, right? And it turns out that the greedy algorithm I just talked about can find well-separated clusters provided that they exist. Okay. Another algorithm that can also find well-separated cluster is single linkage, while perhaps surprisingly other well-known algorithms such as k-means or k-means++ cannot find this with probability 1. Okay. So to me, it's an interesting property and makes it also appealing from a practical point of view. And actually, here at Google, if you came across well-separated clusters that arise naturally in some application, then I'm very eager to find out about this, right? Because now we have a fully dynamic algorithm that can maintain these well-separated clusters, And then this could provide very interesting results. Okay. All right, so one drawback, unfortunately, is that greedy is quite sensitive to outliers. So if we have one point that is far away from everything, this will be selected as center, and of course, this is not what we would like to have, right, in practice. We would like maybe to remove this point, forget about it, and cluster the rest, okay? So, but fortunately, there are variants of k-center that deal with the case with outliers as well. So then we would have a pre-approximation algorithm for this problem. And so this also makes it nice, right? Okay, so I hope I convinced you that this is interesting also from a practical point of view, right? At least potentially. All right, so here at Google, I could find a few papers with this, I guess. I hope I'm not missing some interesting paper in case you just published a paper on this, or maybe I missed about it, let me know, right? I'm very eager to find out. Also, at least this shows that there's some interest in this problem here, and that's the right place to talk about it. We would like to do it in a dynamic setting. So what has been done here for this problem? All right, so there's a paper published at iCalc in 2016, which focused on the sliding window model, right? Which is not really, so it's quite a restrictive case. We don't allow arbitrary insertions or deletions, right? We only maintain the points, say the most recent k points in a sliding window, okay? So we would like to do something more general than this. We would like to deal with arbitrary insertions and deletions. And this is what the rest of this talk is about. Why would we like to do that? Well, in many real-world applications, right, this is actually the case. So for example, think about, right, the case when you cluster maybe YouTube videos, right? Some of these videos might have to be deleted because, you know, maybe they've been flagged as inappropriate, right? Or maybe due to privacy concerns, right? So you don't want to recluster everything from scratch, right? You would like somehow to reconstruct a new solution while taking advantage of what you have been doing, right? Also, the case where we would like to cluster trajectories, right? So meaning putting in the same cluster trajectories that are more or less similar. We'll come back to this point later. So if you want to do that, then the sliding window model is poor. It cannot deal with this, okay? So that's another case, right, where we would like to do something better than clustering, than the sliding window model. And overall, I could find very few fully dynamic clustering algorithms. So if you came across about some interesting problem that would be nice, right, to adapt in a fully dynamic environment, I'm eager to find out. That would be very, very nice. Okay, so so this is our roadmap for the rest of the talk. I'm going to talk about the algorithm for fully dynamic clustering. I will also try to sketch the proof. I never did it for this problem, so it will be an experiment. Let's see how it goes. And then I'll show you some experiments showing also that these algorithms works well in practice, right? Okay, and then talk about some conclusions and future work. Okay, so we want to do fully dynamic, right? But what do I mean by fully dynamic? All right, so we are assuming that there is an adversary, which is depicted here by this little devil. So this little devil decides the sequence of update operations up front before our algorithm starts. Okay? So it decides, okay, I want to add this point, then this other point, then I want to remove P1, and so on. This is decided before our algorithm starts. Okay? Our algorithm does not know the sequence of operations. We don't make any assumption of this. However, we assume that the adversary cannot predict the random choices of the algorithm. Okay? So in practice, maybe if you want, this is equivalent to assume that we have a very good pseudo-random number generator. Okay. Okay, so this is the fully dynamic model we are going to assume. Okay, so of course there is a very simple naive algorithm for this problem. Okay, simply whenever you insert a new point or you delete it, you just apply the greedy algorithm I talked about before, right? and then you're able to maintain a 2 approximation solution. However, the cost per operation will be theta of k times n, where n is the maximum input size. Okay, so if n is very large, then of course this is not feasible, it's too expensive, right? We would like to do something much better than that. Okay. Okay, so let's see, right? Let's move a step further toward a dynamic algorithm. The first thing we do, which happens to be useful often in my experience, right, for parallel algorithms, distributed algorithms, and dynamic ones, is to bucketize. Okay? So we have the set dmin, the interval dmin dmax, where dmin is the minimum distance between any 2 points in input, and dmax is the maximum distance. So we bucketize this set, and we obtain a set gamma, which contains dmin times 1 plus epsilon, dmin times 1 plus epsilon squared, and so on, until we obtain dmax. Okay? So the cardinality of gamma, of course, is log delta divided by epsilon, where delta is the relation between dmax and dmin. And basically, these are all guesses, right? We guess the value of an optimal solution, and all our guesses will be in gamma. Okay. All right. So for each such a guess, so for each value r in gamma, we either show that there is no clustering with maximum radius r, or we compute a clustering in maximum radius 2 times r. And I'm going to show you how to do that. Okay. But now, right? For now, you agree with me, right? That if I can do that, and then I try all possible values in gamma, right? And I consider the smallest value such that I'm able to cluster the points with the radius to r, then I get a 2 plus epsilon approximation, right? Because I have a certificate that I cannot do better, right? Okay. Okay, so now for the rest of the talk, we're going to assume that we fix r, right? And we deal with each r separately. Okay. Okay, so let's see. So we fix r. Let's consider a static algorithm for this problem. And this is very simple to the greedy algorithm we just saw before, right? So we do the following. So repeat until x becomes empty or k clusters are formed. We repeat the following, right? We pick one point arbitrarily, and we make it a center. Okay. Now we create a cluster C with x and dot points at distance 2 times r from x. Okay. We remove C from x, and we iterate until x becomes empty or k clusters are formed. Okay. All right. So now you agree with me that if all points are clustered, then by construction we have a clustering with maximum radius 2 times r, right? By construction. Now, if we are not able to cluster all points, then we have a certificate. We have k plus 1 points that are mutually pairwise distance larger than 2 times r by definition. So at least 2 of these points should end up in the same cluster, and then we cannot have a solution with maximum radius smaller than r, right? Okay. Okay, so very simple. So now, one step further, let's make it a bit more dynamic, okay? So insertions are very easy to deal with. So suppose we want to insert a point x. The first thing to do, right, is to check whether there is a center at distance 2 times r from x. If this is the case, we can put it in a cluster, no problem. If this is not possible, and we have at most k clusters, then we have space for creating a new cluster, right? X will be the center of this new cluster, and then we're still fine, right? We can still maintain a invariant that either we have clusters with maximum radius to r, or we have the certificate. And we have a certificate in case the previous two fail, right? In that case, we have k plus 1 points at pairwise distance larger than 2 times r, and then we have the certificate. So insertions are easy. piece of cake, right? Okay, so what about deletions? Things are still easy if we assume that points are deleted randomly. Randomly, I mean that at each step, right? One point, the point that is deleted is chosen uniformly at random from the current set of points. Okay. So what do we do in this case? Very simple. So if the point we are going to delete is not a center, no problem. We just delete it from the cluster, right? If it is a center, we recluster everything. That is very expensive. It's true, but this happens with probability k divided by cardinality of x. Because we have k centers, right? And the probability that we select that the point that is deleted, right, is the center is k divided by the cardinality of x. Okay? So then the expected amortized cost per operation in this case is k squared. Okay? All right. So this is very simple, but here deletions are random. Okay? So we're still not happy with this, right? We would like to do something better. And in particular, right, to convince you that this can be very bad, consider this case. Consider, right, the case where we have 5 clusters, okay? And suppose that our adversary decides to make our life not easy, all right? So the adversary does not know which center we are going to choose, right? Because it's somehow random. But what it does know is that, for example, in this cluster over here, in the upper right corner, there must be at least one center if we want to have a good approximation guarantee, right? So the adversary can then decide to add these points, remove them, insert them back again, right? And every time, with only 4 deletions or insertions, we would have to recluster everything, okay? So after a small constant number of operations, we would incur of a cost of k times the cardinality of x, which is bad, right? So the adversary, although it doesn't know which points is selected as center, can make our life pretty bad, okay? Okay? All right, so that is not, we can do better. We need to do better. Okay, so let's see what we do. All right, so the algorithm is pretty simple, and it's based on a very simple trick that we're going to reveal now, right?
Just one question.
Sure.
Are you assuming that R is changing over time or not?
All right, so here we are assuming, so we run our algorithm for any R in gamma, where gamma is the set I showed you in the beginning. Oh, sorry. This one here, right? Okay? So you run this algorithm for any value in gamma.
Right.
So you can assume that R doesn't change, right? You just focus on a given value of R, and you apply the algorithm I told you before, right?
But if an insertion causes the chosen R to change, what do you do in that case?
You just need to maintain the invariant that either you have a clustering with maximum radius 2 times R, or you have a certificate. And if you maintain this for any given R
so you
in gamma,
maintain this for every R,
right? Then you can reconstruct, see what is the smallest R, such that, right, you have a clustering, and this will give you 2 types of approximation. Okay? Other questions?
So you assume that dmin and dmax is the global minimum
Exactly.
and maximum of all the future points.
Exactly. This is what we're assuming. Then that would be interesting, probably with some engineering or maybe with some other trick. You can see, right, if the min and the max changes over time, right?
Yeah.
But here we are assuming that every 2 points in input will not be a distance smaller than the min or larger than the max. Right? Okay.
So all of the costs will have to be multiplied by this log delta term, right?
Yes, yes. I'll show you later on, right, what is the amortized cost. Okay. Okay, all right, so let's see. I showed you before, right, the model where we have arbitrary insertions and random deletions. Let's see if we can do something better. Insertions. No need to change. We can use exactly the same algorithm we used before. Okay. Let's see for deletions. Again, if X is not a center, we can delete it from its cluster. No problem, right? We can still maintain the invariance, right? Let's see what we do now. The most interesting case comes, right? So let's fix an order, an arbitrary order on the clusters. And let's say we have C1, C2, CK. Okay? And we denote with U the unclustered points, right? We do this for every R, right? So there might be some value of R such that we were not able to cluster all the points, right? Okay, so now we are going to recluster only the points in CI union CI plus 1 union CI plus 2 and CK union the unclustered points. Okay? These are all the points that will be reclustered. We do not recluster C1, C2 up to CI, where I is the cluster with center that is that we are going to remove. Okay? I'll show you a picture later on.
So unclustered, every time you remove a center, everything that is in this cluster becomes unclustered. Is this correct?
Yeah, until you recluster right after.
Yeah, okay.
Okay? I'll show you a picture later on in case. Yeah. Okay, so how do I recluster, right? So now I just told you which points we are going to recluster. How do I recluster? So at each step, right, I pick one center uniformly at random from this set U hat, right, which is CI, C plus 1, union U, and so on, right? I make it a center. I create a cluster CJ with CJ, containing CJ, and all the points at distance 2R from CJ, right? I remove CJ from this set of points. Now these points are clustered, and then I iterate until I get back K clusters, and eventually a set of points that are not clustered. Okay, so let's see maybe a picture just to make sure we are on the same page. All right, so again, let's consider these clusters over here. Let's see what our algorithm does, right? All right, so let's fix an order. So we have C1, C2, C3, C4, C5. Okay, and let's suppose that the green points are the centers of the clusters. Okay, so now suppose we are going to remove this center over here, the center of C3. So now I'm going to recluster only the points in C3, C4, and C5. Okay, so I'm going to recluster only the yellow points. Okay, and I do it as follows. At each point, at each step, I pick one point uniformly at random, so the green point over there. And notice that this point has been selected with probability 1 divided by 15, where 15 is the number of yellow points, right? Because all of these points, all the yellow points are candidates. Okay? And now I iterate. Okay? So now I pick one point uniformly at random from the yellow points. Okay? So for example, I pick this point over here. Yeah. This point now has been selected with probability 1 divided by 11 because I have 11 candidates, right? And so on and so forth. Okay? So now I got back K clusters and I saw. So now I highlighted the fact, highlighted the probability, because this is what we are going to use in our amortized analysis. We are going to use the fact that although reclustering all the yellow points is expensive, this happens with probability, with small probability. Okay? So in particular, if the adversary decided to remove this point, for example, this point becomes center with probability 1 divided by 15, and the cost to recluster everything here is 15 times K, right? So the 15 cancels out, and then our amortized cost is K, order of K. Okay? That is the main idea. So later on, I'll show you the details, right? But that is the trick we use, basically. Now we have to be a bit more careful because in the meanwhile, we might have added some other points, right? So the probability here does not change, but then, at some point when we are going to delete this, we might have added 1,000 points, okay? So the points that are added afterwards have to be dealt with in a different way in our analysis, okay? All right, so I'll give you some details of the analysis. Let's see how it goes. I hope I will be able to deliver the main idea, but I hope I already got a sense of what is going on here, right? Okay, so let's see the analysis.
Just want to check, make sure that I'm on track.
Yeah.
The only place where you're using the randomness is then when you're doing the reclustering.
Yes.
The initial assignment it was essentially completely deterministic. It's only once they delete the adversary deletes a center, then randomness gets introduced because of the order that you select points in the reclustering.
Yeah, you can think that maybe you start with a cluster, right? And this has been determined deterministically, right? And then you introduce the randomness only when you remove the center. Yeah, you can think about it like this. Okay, but I was thinking more in the case where we start with the empty set, right? And
But then the first point that's going to be inserted will be a center.
Yes.
And then the first point that's more than 2R away from it will be the next center.
Yes, exactly. Sure, you're right. Then we're going to use also in that case, the randomness only when we delete the center. Yes, great. Okay. All right, so let's see how the analysis works, right? So amortized cost analysis. So we want to show that the ratio between the number of operations performed by our algorithm and the number of update operations is small. Okay, so it's small. So we're going to use a charging scheme, right? Where we distribute the cost incurred at each step t between two quantities, ft and zt, and I'm going to define this later. And we analyze each of these quantities separately. So now to remind you, right? You remember we had a problem when new points are added after a center was selected, right? The idea is that ft takes care of the new points, and zt takes care of the old points, those that were possible candidates. Okay? Okay, but now we will see better, right? Okay. All right, so let's see first the charging scheme. So whenever we insert a point or remove a non-center, so in that case, the cost of our algorithm is constant. Okay? So no need to worry, right? We can set ft and zt equal to 0. Okay? Otherwise, let ci be the center being removed. Okay? So if bar x is the set of points that are to be reclustered, right? And this again, remember ci union ci plus 1 union ck union u, then our cost would be k times bar x. Okay? So we distribute this cost among ft and zt as follows. Okay, as I told you before, right? We deal with two cases. In one case, we consider the new points, and the other case, we consider the old points. So we denote with x new the set of points that were inserted after ci was selected as center. Okay? And ft takes care of the new points, and the cost charged to ft is equal to k cardinality of x new. Okay? Now for the old points. So the old points, right? So these are all the points that were already there, were already inserted when ci was chosen as center.
Among the reclassed one always. You're talking only about points that are reclassed, right?
Yes.
Yes, the X bar is the points that are being reclassed.
Yeah, exactly, yes. Yes, exactly.
Oh.
Yeah. Okay, so then in that case, zt is equal to k times the cardinality of x code. Okay, so notice that like if we sum them up, right, we get exactly A times bar X, right? So we're not cheating. We didn't forget about anything, right? Okay, so we now analyze them separately, right? Let's analyze FT first. Okay, so let AT be the number of insertions up to step T included. Okay, so a simple lemma shows that if we sum up all these FTs together, then we get, then we can bound this quantity, right, with AT times K squared. So why this is the case? Well, this follows from the fact that any point U belongs to at most K new sets, okay? In particular, to those whose CIs were centered at the, when U was inserted, okay? Okay, does it make sense? Right? Okay. So then it belongs to at most K sets. Remember our charging scheme, right? Then K times this quantity, and then we get K squared. Okay? So for FT, we are fine. Okay? So now let's see ZT. All right, so the other lemma says that the expected cost of ZT is at most K squared, again. Okay? Let's see why this is the case. It's a bit more technical, but not too much, right? Maybe it's a good time to drink some water. Okay, so we denote with ZIT the cost incurred when the center CI is deleted at the beginning of step T. Okay? So notice that for any T, there is at most one I such that ZIT is not zero. In particular, this corresponds to the center, right, that has been deleted, if any, okay? And we denote with UI the set of points out of which CI was chosen, the unclustered points, okay? Okay, so recall, right, let's go back to the algorithm. So when we selected the CI, right, we selected from this set over here. Now I denote with UI, right, this set here, like the set of possible candidates, okay? All right, so then we are done, right, because we can say that CI was selected as center with probability 1 divided by the cardinality of UI, because all of the points in UI were candidate to be centers, right? This, of course, is true conditioning on UI. Now, it can happen that some of these points might have been deleted afterwards, right? But this doesn't bother us, right? Because then we would have even less cost, okay? Then if we put everything together, we can bound the expected ZIT conditioning on UI as follows. So this is the probability, right, that that point has been selected as center, which is equal to 1 divided by the cardinality of UI, times the cost incurred by the algorithm, which is equal to K times the cardinality of U bar, where U bar is correspond to the set of points, right, after deleting possibly some of them, okay? And then these are at most K, in that U bar is contained in UI, okay? So, I mean, I'm just formalizing what I showed you before in the picture, okay? So the fact that this probability somehow cancels out with the cost incurred by our algorithm.
Can you explain the conditioning a little bit better? Because, for example, this CI, it might have been chosen at a time that U is big, but it might have been chosen as a center anyway later on, right? So you have to take.
All right, so
like for example, if you have a point that's like far away from every other point, the probability that this point being chosen as a center might be 1.
Mm-hmm.
Even though it might have been chosen at the beginning, so the probability at that point is registered as like 1 over a large set.
Yes.
But eventually, the probability that this point is chosen as a center is actually 1.
Yes, but in that case, the reclustering cost would also be small, right?
Right.
Because you would have to recluster just that point.
Yes.
So the idea is that whenever you recluster, and the recluster has cost cardinality of ui, right? Then the probability that that point has been selected as center is also 1 divided by cardinality of ui.
So this is conditioned on the sets.
So conditioning means, right? So, so here, right, when you pick a center CI, this UI can be anything, right? Right. So you condition on one particular scenario, right? So given that when you select that points, you have that set. This means right conditioning, and then of course, right afterwards you. Right, so this is a random variable, and then you compute the expectation of this, right? And this takes into account of all possible scenarios that can happen, right? Does it make sense? Yeah, so in case difficult maybe to explain this, sorry. So in case some detail is missing, feel free to ask, right? So, I mean, this is just, maybe sometimes with pictures, things are more clear, right? So the idea is this, right? That yeah. So I mean, right. Right. Suppose we delete these points, this point over here, right? What is the probability that this is center? The probability that this is a center is 1 divided by 15, right? Or maybe, yeah, all right, maybe it's clear here. Yeah, all right, so was this the point? So this, all right, so the probability that this is deleted, so the probability that this is selected as center is 1 divided by 15. And then I'm going to recluster all these points, okay? And so the probability somehow cancels out with the cost, and we're left only with a factor of k. Now, conditioning on UI means just focus on the scenario where we are going to recluster this set of points. Yeah.
I guess the intuition is that if you have like an outlier that's going to be almost certainly selected as center, it's very unlikely that we pick it at the beginning, where it's going to cost a large cost to recluster everyone after it. It almost certainly is like picked at the end.
Yeah, exactly. That is the thing. Okay. Okay. Yeah. Feel free to ask more questions. Right. I think it's a simple idea and quite powerful. And Mauro, this algorithm works well in practice, right? It's very simple to implement. Right. Okay. All right. Yeah, I hope I was able at least to deliver the main idea. All right. So let's see. Let's put all the things together. Let's see what is the result, right? What we can claim. All right. So we always maintain a 2 plus epsilon approximation, right? Because again, right, we are running this algorithm for any value r belonging to gamma, right? And for each such value, we maintain a clustering, or we have a certificate, all right? So now the smallest r, such that we are able to cluster all points, gives us the 2 plus epsilon approximation, right? The expected time, right, is this quantity, and where this comes from, right? Remember, we showed that both ZT and FT are bounded by this k-squared factor, right? Then we have to multiply by the number of by the cardinality of gamma, right? Because we are going to do this for every element in gamma, right? Space is this quantity basically because we have to store, right, a copy of the input at each level for each value of gamma, for each element in gamma, right? It works in the fully dynamic model, right? Where fully dynamic means, right, what I told you in the beginning. All right, so moreover, if we maintain the data structure I just told you about, right, we are able to test clustering membership in constant time, right? And we can also produce in output all points in the cluster C of a given point in time k plus cardinal accuracy. Okay, so that is I think pretty nice. So query time is good, and moreover we can show that this result not only holds in expectation but also with high probability. Okay, so we can show that the probability that the total time is much larger than the expected time, right, which is here, is small. Okay. So and in order to do this, right, we couldn't just use a Chernoff bound because the random variables are not independent, and we needed a workaround to fix this. We couldn't use a zoom inequality either, right? So we basically adapted the proof of the Chernoff bound to this setting. Perhaps there is a better way to do that. That would be very interesting if you have other suggestions for that.
Is it based on martingale analysis?
No, but if you have an idea on this, that would be interesting. Okay. Okay, so depending on how much time do I have, how much time do I have?
7 minutes.
Oh, all right. So probably I will not. Let me just mention that we can decrease the space requirement even further, right? And here I tell you why. Maybe I can send you the slides in case you're interested. And at the end, right, this is basically the whole picture, right? That compares the related work with our result. Okay. So our result, these first two are our results. The second one is still in progress. So we have a 2 plus epsilon approximation algorithm, and the last one is the ICAL paper, right? The approximation in that case was 6 plus epsilon, and only for the sliding window model. We can show that we can actually have a 2 plus epsilon algorithm approximation guarantee for the fully dynamic model. However, this comes at the cost of much more space. Okay, so here is super linear, while in that case the space was very small. Then we can show that we can decrease the space at the cost of having a worse approximation guarantee. And this result is also interesting because there is a lower bound saying that there is no approximation algorithm with approximation guarantee better than 4 that uses less than n to the power of 1/3 memory, where n is the maximum size of the input. So this is pretty close to that, right? So we are trying to close in the gap between the lower bound and the upper bound, and we are not that far. We are close, right? So it would be nice to actually close the gap in case.
You said n versus versus cube root of n? N to the 1/3?
Yeah, n to the 1/3, yes.
Okay, so somehow being more than linear and less than linear seems like a gap. But
it's a gap, yeah. It's quite a gap, yeah. But you know, like this is at least it shows that if you want to do something better than 6, right? You cannot just have this amount of memory, right?
So I don't quite understand the sliding window result, because it's saying even if your input is n, you just have to keep the sort of the centers. You don't keep the whole input.
Exactly.
Okay.
Exactly.
Yeah, it's also there's a dependence on the maximum distance and minimum distance.
So there's a dependency on delta, which is the ratio between the max and the min.
Okay.
So this seems to be needed also in that case. Again, I think if I remember well, they're also guessing the value of the optimum solution, then they try all possible guesses, and then yeah, it would be interesting to get rid of this dependency also, right? That would be very interesting. Okay, perhaps I will quickly show you some experiments. Feel free to stop me if I really exceed. Right, okay, so we did some experiments, all code and data sets are available, right? So my student did a very good job, right? And everything is available on GitHub. Feel free to use it. Very efficient implementation in C, right? So
it's an interesting username.
That's
an interesting username.
Yeah, that is.
So the problem is that, all right, so that was actually anonymous.
Oh.
And then we wanted to make the code available, but we couldn't reveal our identity, right? And then they became ready, but then the student already left for some company, and then we didn't change the delegate, right? That is the story. So it's still anonymous, but it's still there, right? And the student is eager in replying. So it's really nice, right? But then we didn't manage to change the link. All right, so we could see different data sets, Twitter, Flickr, and also trajectories, right? So these are 83 million points from trajectories performed by around 500 taxis in the city of Porto, in Portugal, okay? And trajectories are updated every 15 seconds. And all right, so once you have trajectory, it is also interesting to see how do you measure the distance between two trajectories, right? And there is some work on this, and in particular, we have the symmetric Hausdorff distance, which is a metric, and that can be used in our setting, right? Still, we have guarantees and everything. Okay, so I will be quick, right? So yeah, thanks for being patient. Right. Okay, so we consider two dynamic environments, right? Sliding window and also taxi trajectories. And in this case, at each point in time, either a new point is added to one trajectory or a new trajectory is created. Now, if you think about it, this sliding window model is poor, cannot deal with this case, because the trajectory that I'm going to update at some point is not necessarily, right, the oldest or the most recent, right? This can happen arbitrarily, right? So sliding window model does not work there. And it's nice because we found practical case, right, where the sliding window model does not work, right? So there's a good motivation for doing it fully dynamic. So, all right, so interesting things to check here is how far we are from the optimum solution in practice, right? And what is the running time, okay? So we came up with a lower bound on the optimal solution, and we compare how far we are from the lower bound. Okay, so let's see, right? So it was a bit tricky. How do we measure this, right? At each point in time, right, you have a new solution. So you don't have just one solution to compare, but you have multiple solutions, right? So the best way we could come up with is to consider the median, the first and third quartile of all the solutions we built throughout the execution of the algorithm, right? So this is the median, right?
Of the approximation.
For the approximation ratio, exactly, right? So the blue ones is us, and the red ones is the sliding window model, right? So remember, right? They have a 6 approximation guarantee. We have a 2 approximation guarantee. And here we show that in practice, we are slightly better than 2, right? It's often the case, right? You can actually do better than what the worst case analysis suggests, right? And they're also better than 6, right? However, the gap is significant between the two approaches, right? So it pays off to use more memory.
So using an epsilon around 0.1?
Yeah, so in that case, it's epsilon 0.1, but here we also change epsilon, okay, right? So, and still it's consistent. Okay, then running time. So running time, we're actually slower, right? And this makes sense. However, the average running time per update is less than half millisecond, right? So still not too bad. Okay, and then we also plot. We wanted to see, right, whether the concentration of measure result also holds in practice, right? Remember, we show that with high probability we're not too far away from the expected value, right? And basically, this histogram is what wants to give a practical, wants to show what happens in practice, right? One way to interpret this is that 60% of the time, right, we have 0.5 seconds, 0.5, 10 to the power of minus 4 seconds, right? Okay, which is pretty good. And also you see that there is concentration, right, on the expectation, right? Things that are far away from the expected value happens with low probability, right? Okay, then we check the same thing for trajectory, and here we actually also plot all the possible running time, right? We basically plot the histogram of the running time of update operations, and basically the bottom line is that 80 million operations require less than 0.004 seconds, okay? So this means that in practice, also the worst case is not too bad, right? Okay, I'm really done. Sorry, thanks a lot for your patience. Let me just conclude by saying that this is close to the best we can do. Approximation guarantee better than 2 is NP hard, right? And we have a 2 plus epsilon approximation guarantee. Less than n to the power of 1/3 memory is not possible for any 4 approx. And we have a 4 approx algorithm that requires slightly more than n. Experimental evaluation was very good. And future work, can we match the lower bound? Can we close the gap, right? Can we adapt other variants of K-center in a fully dynamic environment? Can we deal with the case where we have a batch of updates, right? This is also an interesting direction. Can other clustering algorithms such as K-means plus, facility location, K-media, can be adapted into a fully dynamic environment? That would be very good. And if you have your favorite data mining, machine learning, or graph mining algorithm that would like to adapt in a fully dynamic environment, feel free to ping me. I'm very excited to do that. All right. Thanks a lot for your attention.
Okay, one question. So in your update, you're updating, some number of centers and some fraction of the points. You're basically charging K times N for that update, or K times cardinality of the points that you're updating. But they really only having to look at K minus I centers as the possibility, right? So it's really K minus I. Is there, you just didn't see a way to take advantage of that slight tightening?
Yeah, that's a very good point. We couldn't see how to take advantage of this in the worst case, right? But it's true that, there is, it's largely better than that, yes. Very good point, yes.
Any idea what happens with adaptive adversaries?
Adaptive means?
Observing the algorithm and making the next move based on the move of the algorithm.
Seems like the adaptive is going to just take the center every time.
Yeah, exactly. That is. Oh, you mean an adversary that would know, for example, the random choices of the algorithm, for example?
Not necessarily private random choices, but the centers that the algorithm chooses. For example.
Yeah. Then it would remove the center, and you would have to change completely the approach, right? Because if you remove the center,
is there a lower bound?
That's a very good point. Yeah, that would be interesting to find out. Yeah, very good point. Yeah, if you have ideas, I'm eager to discuss about it. Yeah.
So for K-means plus it seems like the process is quite similar. So may it work or?
Instead
of selecting a random point, let's say one from probability.
Exactly, that's a very good point. The thing that in K-means plus, even if you had the point, you might have to change the solution, right?
Yes, because the probability.
The probability change. So it's much more difficult. So it's not straightforward. But yeah, if you have ideas, that would be very nice. Yeah, very good point. Okay. Thanks a lot. Sorry for taking so much long. I got passionate.